Okay, well, welcome back. I appreciate your patience with me today. I'm in Germany for a conference, so we have 3 time zones represented today. This is lecture 5. We're going to start out by talking a little bit more about Hill rate laws. Then I'm going to talk a little bit about how to translate motifs into rate equations, and then we're going to analyze the autocatalysis reaction, which will be our first example of bistability and bifurcations. So I'm going to start out by explaining how to use variable stoichiometry in Antimony. I'd mentioned it the other day, but hadn't given an example of that. I'm going to show you quickly something that's quite useful, which is a web interface for running models that you can use to convert models from SBML, which is an exchange language, into Antimony and back. And then we'll go ahead with Hill functions and autocatalysis. And then I'd like to maybe talk a little bit about that paper I asked people to look at of Mo and Jensen. So the first thing that I want to talk about is variable stoichiometry. Tellurium Antimony does allow you to change the stoichiometry of chemical reactions, for example, in Hill functions, but there are some oddities to it. In particular, you have to have a different name for the variable for the stoichiometric coefficient each time you use it. So if I look here, the way I denote the variable stoichiometry is by using a variable name and then a space and then the species name, as in here, J1 E plus N S. So that would be, if N were 4, that would be E plus 4S. If N were 6, it would be E plus 6S. I don't know what happens if N isn't an integer. I don't know if that works or not. But if I want ES to go back to E plus NS, that will crash because the letter N is used twice. And so if I want to have ES goes to E plus the same number, I'd have to use a different variable name like M, and then set N and M equal to the same thing. You also cannot change the values of the stoichiometric coefficients directly from Python. You have to do it indirectly using a function that we haven't really talked about. Normally I talk about a little bit later, which is a continuous assignment. Antimony has a number of different kinds of equal sign. The regular equal sign is evaluated only once at the beginning of a simulation, and that means you can overwrite it from Python. Colon equals is continually updated. Effectively, that's a function definition. And so if I set M and N colon equals H, and then I set the value of H equal to the thing that I want, both M and N will change. So you may not need to remember this if you don't, if you're not going to use variable stoichiometry, but it does allow you to change those stoichiometric coefficients without having to edit the string itself. I'm not going to do an exercise on that right at the moment, but it's there if you need to remember how to do it in the future. In the past, people would go through all sorts of edits in the Python to try to actually hand manipulate the Tellurium strings, which is not very, Antimony strings, which is not very convenient. The next thing that I want to talk about is downloading SBML models and converting them to Antimony. There is, if you download an SBML model, you can download it as a string, and there is a function inside of SBML of Antimony, Tellurium, that will do the conversion back and forth between Antimony and SBML. But normally, if you want to actually read SBML, It's not very friendly. You usually use a specialized editor to view it and edit it. It's a lot easier to change SPML models in Antimony because then you can work with them as text. And so what we're going to do as a little exercise is we're going to find a model in biomodels. We'll download it. And here I said upload it to NanoHub. That's not what I want. We're going to use the online editor to do this. Apologize, that's an old slide there. So the first thing that I want to do is have you download an SPML model from biomodels. So why don't you go to the biomodels database. If you search biomodels, you'll find it right away. In the search bar in biomodels, you can find a model that is of interest to you. So you might search almost any biological system you like, probably not something too complicated, but you might try searching for something like cell cycle. Or here I suggested EGFR. Just put in the chat when you've gotten to the biomodels repository and see if you're able to find an EGFR model. That either speak up or put it in the chat. Okay, so you've got several. That's fine. So now pick one. The one that I would recommend to start with would be this Bianconi 2012. Actually can't see. The chat's pretty small on the computer I'm using. I can't see if you've got that one there. Pretty much any one of them should work. Bianconi 2012 is the first one that came up. And that should open a page that looks like this. And if you click on the SPGN link, assuming it's working, it may or may not be working, it should give you a little diagram that shows the architecture of the simulation. Did it do it? Just let me know in the chat if that worked or not. Or if you need more time. Up. As I say, it doesn't do a very pretty job of laying it out. So you'll get a mess like that. Now, if you go to the model and select the Files tab, you should have a list of files. And normally the first one in the list will say model file, and that will be the SPML version of it. And so download that, and you should have a copy of the model. I'll do this in a more convenient way in just a minute, if it works. Sometimes the the interfaces don't work, so we better have a backup on this. Okay, were you able to get it to download? Okay. Okay. So not going to do it through NanoHub. I'll just walk you through the because we're not using NanoHub this time. I'm sorry about this. I thought I had corrected this in the in my deck. I must have a different version of the talk that I should be using instead. But we can open that XML in Antimony if we do the following. So go into your Colab, since we're using Colab rather than Antimony, and then you can do a R equals TE load SBML model instead of TE load A, and then give the file name. Then you type antimony model equals r dot get antimony open close parenthesis, and then if you print it, you'll have converted that SBML to an antimony model. See if that works for you. If it doesn't work for you, I'll show you a better way to do it. So I'm not going to take a lot of time on that. But that's the traditional way of doing this. You may get quite a bit of code that doesn't look terribly familiar, which is associated with layout and other things in the SBML. And so there may be quite a bit that you don't care about that's in that file, but it should in fact run. If you have trouble with the file reference in Colab, if you just put in, let's see if I can see what you just wrote. Okay, great. I have a rather small laptop with me on this trip, and so seeing the things that you put in the chat, it just takes a little bit of an effort. It's still a great way to communicate, but it does mean that I have a little bit of extra manipulating to do. Okay. Niraj, did that work for you?
No, I'm getting some error actually.
Okay, well, let's see if the other way works. And if the other way doesn't work, then we'll come back and we'll debug this one. Okay.
Okay.
Okay. Okay. So if you've got it working, now you should be able to type r.simulate, for example, 0 to 10,000, and r.plot, and you should actually be able to run that simulation. Niraj, what was the error you were getting?
Could not open the .xml file as a file or URI. Runtime error basically.
Hmm. So you were able to download it,
Yes.
but Colab wouldn't let you open it.
I'm actually running on VS Code. I'm not sure if that
Ah,
is something.
no. Well, so in that case, what I would suggest you do, it's a little bit less convenient, but open the XML in
Right.
Notepad, some editor,
Okay.
copy all of it,
Mm,
and where you type the instead of trying to actually open the file, where you type load SPML model,
right.
put triple quotes, paste in the full SPML string, triple quotes, and then do it that way.
Okay, so I have opened the file. I need to copy this.
Right. Put it into a string in Python.
Okay. Okay.
And then instead of TE load SPML model quote file name, have TE load SPML model string. See if that works.
Okay.
Again, if it doesn't work, we'll do it an easier way in just a second.
Yeah, it works.
Great. Were you able to run it then?
Yeah, I'm just running. Yeah, I was
Great.
able to plot.
Perfect. Okay. The other thing that we have, which is a fairly new tool, was written by Herbert Sauer's group last year, is a tool that lets you translate back and forth automatically. And it actually has a search bar for biomodels, so you don't even have to download the file. So look for sys-bio.github.io/make SBML. And that should open in your browser, should open a window that looks like this. Let me know when you've got that open.
Yeah, got that.
Great. Okay, both. Okay. Okay. And now we can go back to use the search bar to run an SPML model. So here it actually says, oh, sorry. Apologize again. This has the old syntax for the NanoHub. So what I want you to do instead is here in the search tool, in the search bar, type the name of a biological function. For example, why don't we use FGF? Type FGF there. Turn, it should pull up a whole bunch of different options. Then if you use the arrow pointing to the left, it will convert the SPML to antimony. And similarly, if you opened this window and you had antimony code, pasted it in the window on the right, it will convert it to SPML. So yeah, Gold Better 2008 would be fine. See, you have some options: save antimony to file, copy antimony to clipboard, save SPML to file, save SPML to clipboard.
So we select save antimony to file, right?
Let's see, let me do it. Let me do it myself. Okay. So you're seeing the make SPML models page. So let's see, I'll type FGF, return. That gives me some options. I'll try the first Goldbetter 2008. And it'll pop up the XML on the left and the antimony version of it on the right. Did that work for you?
Yep.
So if you actually want to run it, let's see whether we have in the screen, make this. My window's a little bit crowded here, so let's see. Okay. So you should be able to see that. So now you can, if you find a model that you like that's in SPML, you can pull it into Antimony. So I hope that's a helpful tool when you're looking around at possible models to run. Anything that exists in SPML, we can convert pretty easily. So that was what I wanted to say about that. If you want to run it, you can either copy or save that antimony model into a string or into a file, and then you should be able to run it using TE load A now in your Tellurium notebook. If you're running in VS Code, it's fine. If you're running in Colab, that's fine too. So why don't I give you a minute to pick a model and then see if you can get that to run. I'll tell you, occasionally they won't. Sometimes the models on that biomodels repository assume additional information that's not present actually in the SPML. And so occasionally I've picked models that were supposed to be validated, but in fact required additional things. So they don't work automatically. Again, I apologize for the references to NanoHub. Last year we still taught this through NanoHub, and I've been going through the older slides and scrubbing NanoHub from them, but I guess I missed this one. It may seem pretty straightforward that you ought to be able to download and run a model, but in practice, when people publish models, it's usually pretty hard to replicate them. And so the ability to do that with a few buttons, clicks, is actually pretty impressive on the part of the teams that put this together. Yeah, looks great. Okay. Good. Anything else we want to discuss about this, or can move on? Great, wonderful. Okay, that's fine too. Okay. I want to remind you again about how we're going to select columns when we do the r.simulate function. We just make a list and we put the names of the variables that we want to output in the list. Often the first line will be the first column will be time. Often the others are species names, but they might also be rates, J1, J2, J3, and so on. When we do that and we run simulations repeatedly for the same number of time steps, we can then use an hstack, numpy hstack, to append columns if we want to plot a lot of time series together instead of overlaying the plots. Sometimes that's more convenient if we're going to do post-processing than it is to keep them as separate files. And so we used hstack to build a little parameter scan in Tellurium. Again, there are probably more elegant ways of doing it besides hstack. Plenty of different ways of combining arrays in Python. So I learned how to use vstack. And again, there are multiple ways to do that. You can also use appends instead, if you'd rather. Depends whether you'd rather work with lists or with numpy arrays. If you work with lists, then you have to convert them to numpy arrays before you use numpy on them. Only thing I have to remember is that array equals numpy empty. And these days, of course, with Copilot or any of the AI tools, you don't really have to remember those things anymore. So it's a lot more convenient. Say, give me an empty array of dimension 0, 2, and it'll give you the syntax for it. You don't have to remember the code. And we also calculated steady state values. The steady state values, as I mentioned, doesn't always work. There's an option, conserved moiety analysis, which sometimes helps. If you set that equal to true, sometimes the steady state analysis will work better. We saw something in the simulation the other day where we had a value of P that was increasing continuously in time, which meant that the system never reached steady state. So we had to get rid of that for steady state analysis to work. Sometimes it's just easier to run the simulation for a long time until it reaches steady state. Of course, you may waste time or you may not quite reach steady state depending on how long a time you pick. And so if you can get the steady state analysis to work, it's more reliable. In this case, we were using vstack to assemble the parameter value on the left and the steady state values on the right to accumulate the steady state value as a function of the parameter. And then we were plotting a fixed point in this case, the rate of production of P in this case versus the value of S for the Michaelis enzymatic reaction. And that's code that you should have. I'd open that one up from the other day if you have it, so that we have it available. If you don't have it, it's in the student materials in this Michaelis-Menten steady state vstack folder, that notebook that you can use. So we calculated the Michaelis-Menten rate law analytically, and then we showed that, in fact, if we restricted the amount of S to be constant, that we got the rate of P. Increase of P was, in fact, the Michaelis function of S. We did the same derivation for multiple cooperative reactions. In this case, we have E plus N molecules of S going to E S sub N, and then that decaying to E plus P. If the rate obeys mass action, Kf times E times S to the N, then we get the Hill function for the dependence of the production of P on the concentration of S. It's a little more tedious, although it's interesting to write that cascade reaction that I drew there and compare the result. At long time, the steady state will be the same. At short times, the two are quite different. So let's come back to that and just do it again quickly. If you have your code from last week, that's fine. So write E plus N times S goes to KFE to the times S to the N, and so on. And reproduce it. If you don't want to do that and you don't have it with you, it's Hill steady state of vstack. So I'll wait for people to get that open because we'll use it going forward in the class. So the code looked like this. We had our basic enzymatic reaction here. Yeah, perfect. And then we turned on conserved moiety analysis, created an empty array, scanned here S between 0 and 5 at steps of 0.1. You can here, I think, Niraj scanned from 0 to 10. That's fine too. Used r.reset. Every time you run the simulation again, if you don't want it to continue from where it was, you need to do a reset. Overwrite the value of S. Here, get the steady state value, stack the result onto our array, and then plot the result. You could also use an append and then convert it to a numpy array before you plot it. That would work just as well. And avoid the annoyance of the empty array and the vstack. So here, actually, this is another slightly old slide. It says we can't change the stoichiometry of the chemical reaction, but let's not try to change the stoichiometry by hand. We could, but we don't have to. Notice that S has got a $sign in front of it, so 4 times S, $4 S, and 4S doesn't actually make any difference to what happens. So we will try what happens if you now make a loop and try the value of N being 1, 2, 3, 4, 5, 10, and 20. Okay, is that clear? Give that a shot. And plot them on top of each other. So you'll put this loop that you have here inside of another loop where, in addition to overwriting the value of S, you're going to overwrite the value of N. Means in particular in line J1, you're going to have to change the S to the 4th to S to the N, and then pass the value of N from outside. If you want to use the overwriting of the stoichiometry, what you would have to do is you'd replace this number 4 by a variable name like M, and you'd have to in J1, and you'd also have to replace the 4 by a different variable name like M2 in J2, and then set both M1 and M2 colon equals the variable name that you want to assign them to. So it's a little bit, the syntax would be a little bit awkward, but you could do it. You could have something like I'll type it in the chat. That works for you. If it doesn't, don't try to change the 4s. Just change don't change the 4s in the stoichiometry. Just change the 4 in the rate law. It doesn't make any difference. The outcome of the simulation won't change, whether you change those 4s in the stoichiometry or not. In this case, you're running at 2 loops, so the simulation can take a few minutes to run, depending on the resolution of the scans you do.
I'm sort of getting the same graph somehow.
Right, let's see. You have to overwrite the value of R of H after the reset. And of course you have to change the 4 to an H in the J1 function. Also, if you want them to overlay each other, in this case, the way you're doing it, you'll have to do a show equals false inside of the loop, and then a show equals true outside to get the plots to come out on top of each other. Although it's not absolutely essential to do that.
Yeah, I'm still yet getting the same plots.
You want to screen share for a second?
Yeah, sure.
Okay, I see. Look in line J1.
Okay, we are only solving for J1.
Right, but if you look at the rate, you have S to the 4th. It should be S to the N or S to the H.
Oh, right. Got it.
There. I think you probably want to make that okay. Yes, okay, try that.
Symbol and physically stored and what.
Yeah, so you have to go back up, make it H. Because you can't use the same variable name as the ones in the other. If you use the variable name for the stoichiometry, you can't use it anywhere else.
Okay.
Okay. Well, that's the H equals 1 case.
Yeah.
Taking a little long. 2, that's fine. Now, if you wanted to plot them on top of each other, you would use a show equals false inside of the plot array, and then do a show equals true at the end.
So like after the 2 loops, right?
Outside of the loop. And I have
Both
to,
the loops.
yeah. Yeah, T dot show, I think. I think it's just T dot show, isn't it? Pedro, do you remember? I think it's show.
But yeah.
But you can see the change. I'll let you play with the plotting option on your own.
Yeah, sure.
But there are a variety of ways you could do it. Yeah, that's right. Pedro says if you put the last plot with show equals true at the end, that should work. So here, at the end, just copy the T plot array line one time. And just repeat that with show equals true. Just change show equals true. Leave it exact. Just exactly as it was.
Okay, exactly.
Just change show equals true. It'll overwrite itself. It won't do anything else. There we go. Okay, and
yeah, again, it will take a lot of time, so I'll maybe plot it.
Yeah. Well, why don't we, how many did you ask it to do?
So I exactly 1, 2, 3, 4, 5, 6, 7 different H values.
Okay, so why don't we just in that A range, just to speed things up in the 4S and npi.a range, make it 0.5. It won't be very pretty, but it'll run faster, and we can just make sure that the code works. Okay, try that. String literal has a quotation that's not matched. Should probably have had to do something like plot the value of h each time so we knew where it was, but there it goes. Great. Okay. So you can make that prettier, but you've got the basic thing working.
Yeah.
Shannon, is that okay for you too?
No, I keep getting the same error. Like it says the symbol M is not physically stored in model data structure.
Okay. So why don't you screen share too? I can show you
sure,
why
sure.
that's the same issue. That the variable stoichiometry is a new addition to tellurium and antimony, and it's a little dodgy. So I'll show you how to. I'm sure it's the same thing that we just had. So let's fit that working. Okay. So yes. So you see in line 101.
Yeah.
You say E plus M times M molecules of S, and then you have 5 to the S to the M at the end of that line. You can't use M twice. So if you call that M2 or something like that, something different, now you have to set also M2 equals H. M2 colon equals H. Now that should work. There you
go. N is not a name, the species reference.
Let's see. Where is it? And sorry, the error was what again?
It says N is not a name, the species reference. Here it is.
Species reference. Huh. That one. Try calling it something like N1 instead of N. And then change it in line 113. Same thing.
Yeah, same thing.
Huh. So it's okay with M, but not N. Why don't we just take out that N1 and see if it works after that? You can leave the other one and it won't do anything.
Cannot perform moiety conversion.
Okay, so that's the answer. Okay, so all right, so it's telling us line 1, so we can't use line 116. So you have to take line 116 out. I didn't know that. This is the danger of using a new feature.
Wait. Steady state value is raising another error.
Cannot be shown. Okay, go back to the line, turn on line 116 again and set it equal to false instead of true. I don't want to take too much time on this because it's not something we're going to do very regularly. What does it say? Cannot either set third point and else equals false. Okay. Oh, we have to put that inside of the after the reset. We have to put line
Oh,
116 after the reset.
After the reset.
Yeah.
Nope.
Still not.
Oh, this is weird. The code is exactly the same as in Rush, so I don't understand.
Well, I apologize. I genuinely don't know what the issue is here. Wonder, and you're running it in
Locally. Maybe the version is different.
I wonder if it's an older version of Antimony. I apologize. I don't know what to do here. I don't want to take. This is not something we're going to do very often, so I don't want to take too much time debugging it.
Okay, sure.
Is that Niraj's code there?
Yeah, maybe I just copy pasted my exact code what I used.
Okay. Do you want to try running Niraj's code once just to make sure?
Yeah. I'm trying.
It worked for me in Colab.
Oh, it worked.
It did work.
Yeah, it worked. But why? Oh, okay. Okay, I will figure that out later.
I apologize. That one, this is you. Sometimes you know about as much as I do or more. This is not a feature I've used very often, and so I can't. I'm actually quite puzzled by that myself. I'm not sure where the I'm not sure where the issue is. Okay, so remember that we did the derivation of the Hill function where we said the rate of production of P was R times E total times S to the N divided by K to the N plus S to the N. We defined the maximum rate as R times E total, and that gave us the classic Hill function V max S to the N over K to the N plus S to the N. Different set of N's, but I actually have a function called plot Hill function in the demos that goes just N equals 1, 2, 3, 4, 5, 6, 7, 8, 9. And what you'll see is that N equals 1 gives you the Michaelis result, and N equals 9 gives you a fairly steep sigmoid. As you increase the value of N, you get a sharper and sharper step function. For typical biological systems, we typically use an N of 4 or an N of 8. If you want things to be really Boolean, an N of 20 essentially is a step function. Now, there are various ways of scaling the Hill function. You could define a reference Hill function, which was x to the n over 0.5 to the n plus x to the n. That'll scale between 0 and 1. If you want to interconnect things, that's useful to be able to do that. You can also have non-integer exponents. you're allowed to have an n of a half, 1.5, and so on. Those have sometimes interesting properties. But fundamentally, if you have s to the n over k to the n plus s to the n, if n is less than or equal to 1, the value at 0 is always 0. The value at k is always a half. The value at infinity is always going to be 1. But it differs. If you have n less than or equal to 1, the slope is maximal at 0, and it's got a value of 1 over k to the n minus 1. And then value at k, at the slope at k is intermediate for small n and maximal for large n. So you go from a convex to a sigmoidal shape as you make n greater than 1. So for a larger n, you get a more step-like function. Again, if you make n large enough, you get basically a step function, a Boolean function. If you have a series of phosphorylation events, the net effect of all those phosphorylations gives you a high cooperativity, a large value of n. So you get switching, sharp switching as you change the concentration of the thing activating the system, which is often a biologically useful function. In many experimental cases, you wind up fitting the observed response curve with to the value of n, and so you may not always have a value of n that's an integer. A nice thing about Hill function is that you can easily replace an increasing Hill function by the decreasing Hill function simply by replacing the x in the numerator by k, and you get then a decreasing Hill function which has exactly the same behaviors, except that it is 1 at 0, decreases to 0 at infinity, still a half at a k, and still has the sigmoidal shape. And so now we can quickly go back and forth between increasing and decreasing functions, because these are going to represent regulation by just changing one symbol, namely whether we have k or species concentration in the numerator. This is just the equivalent properties for the decreasing Hill function. So now let's do one simple example. We have running, we hope, the case of the enzymatic reaction here. Let's compare the time series of it, not the steady state, but the time series of it, to the Hill approximation. So take the you've already written, and now write E plus n times s goes to V max s to the n over k to the n plus s to the n goes to E plus p, and set kn equal to kr plus r over kf, V max equals r times E total, and try that for n equals 4, E0 equals 1, S0 equals 1, start out with everything else 0, and set k forward, k backward, and r equal to 1. If you plot all the columns, it gets confusing. So the first time, plot just ESN and P versus time. And then the second time, just plot the rate of production of P, which would be, I think, J3, and time, and see what happens. Compare the two. So you're not using anything fancy here. Did it here just by creating a J4, where I had my new equation in as J4, if I do that, I see that ES does not stay constant, 1. And 2, at short times, the rate of production of P here, which is J3 or J4, J3 for the Hill equation, J3 for the enzymatic reaction, J4 for the Hill equation. They're very different, about as different as they could be. At intermediate times, between about 1 and 4, they're pretty comparable. And then at long times, they both go to 0. Did you get something that looked like that?
Can you explain the equation J4 itself?
So what we have here is, what we want to know is what the rate of production of the product is as a function of the concentration of S
Right.
and the concentration of enzyme. And so in the first one, we have the enzymatic reaction we already wrote down. In the second one, we're writing directly E plus N molecules of S goes to E plus the product. And I've given the product this different name because I don't want them to overlap. I really should have written EA plus NSA goes to EA plus PA so that they don't collide with each other if I put them in the same function. And so if I look at line 12 here, J4, EA plus 4 molecules of SA goes to EA plus PA. And the rate is given by Vmax. Vmax is R times E total, R times EA, plus times SA to the 4th, divided by, and now I have to get the value of K, because K is a little bit funny here. Kn to the n is Kr plus R over Kf, so I have to read that off. K2 plus R over K1 plus SA to the 4th. We know that the enzymatic reaction only behaves like a Hill rate law at long times. And so we don't expect them to agree at short times. We're short-circuiting. We're saying if we replace the true enzymatic reaction with a Hill rate law, how much of an error do we make? That's the question we're trying to answer. Did it work for you, or is it not working?
No, I'm still waiting.
Okay. So maybe it'll be clear if we go to the next step, which is now use the $sign to fix the concentration of S. Now what do you see? Because remember, we're assuming that the Hill function is assuming that the amount of S is large compared to the amount of enzyme. And so the way we approximate that is by saying the amount of S doesn't change. The amount of substrate doesn't change. Now you should see something very different from what you got before. What do you get? So all you have to do, if you go back here, all you have to do is put a $sign in front of S in line 9, $sign in front of SA in line 12. You run it again. Especially look at this one where we have dp by dt versus time. What happens? Now, you should see that dp by dt for the enzymatic reaction takes some time for it to reach its steady state. For the second equation, it always is that value. But now they're identical. So in this case, what we've shown is that, in fact, provided you wait long enough, you wait an equilibration time, the enzymatic reaction gives you exactly the same thing as the Hill function. So as long as you wait, here it takes about 1 time unit. As long as you wait more than that, the rates are the same. Something that you could do on your own here, if you've got this running, would be to change the values of Kr, R, and Kf and ask which of those values determines how long it takes for the system to equilibrate. How long does it take before the two things are the same? Because that'll tell you whether you're allowed to use that approximation or not. Any questions about that? If you look at the steady state values, they're identical. So this is telling you that the approximation really works. Since we did it analytically, it ought to work, but maybe it takes a little bit of time. Now, I did in the past do the analytics. Yeah, there you go. I did in the past do the analytics to do the exponential convergence of this. I don't think I want to do that today because there's some more interesting things I'd like to talk about. Yeah, here it is. I did do it. You can actually solve analytically. I'm not going to do the derivation, but you can solve analytically the difference between the J3 rate and the J4 rate, and you get an equilibration time, which is tau. And the equilibration time happens to be a little bit complicated. It's given by, actually, let's not, I don't want to do this one here. I think I'm going to skip this. You can come back to it if you like. Let's just say it this way. If you have more S, it converges faster. If you have more bigger K, it converges faster. If you have more E, it converges slower. And you can, I'm not going to ask you to do these exercises. I don't think it's worth, there are more interesting things to do. You can come back and look at these, but there is an exercise that you can play with, a Hillen's enzyme convergence time that actually calculates all of this. I'd like to come now instead. Do you want to take a break, a short break? Or do you want to keep going? because once we have Hill functions, we can begin to do some interesting things. And so I'd like to actually, I apologize for skipping that exercise, but I'd rather get to something that's more biologically meaningful where we can use that result. So I sent around a homework assignment, which is actually in Herbert's very first chapter, where he gives us 5 motifs: autoinhibition, autocatalysis, cross inhibition and activation with autocatalysis, cross activation with self-activation, and cross inhibition with self-activation. The question is, what are the behaviors of these circuits? Because all of these are classic circuits that you get both in signaling and gene regulatory networks. Now, I asked you to do 4 things, one of which was display the time series for A and B for initial values of A and B being different. Then do parameter scan for A and B much less than the K in the Hill function, round equal to K and greater than K. This one was change the other key parameters, the rate constants and the Ks. And the last one, which I don't really expect you to do, sort of an extra credit, is to ask if you have a perturbation of the system. Do you come back to your original value or not? And I'd like to work one of these with you in class, number B, which is the auto activation, because that really begins to introduce some fundamental ideas. So when you're going to model signaling and regulatory networks, there's a lot we don't know. And we're going to normally use Hill functions to represent our ignorance about how those things work. And so when we model the effect of an activator and inhibitor, we're normally going to be modifying the velocity of the reaction with a Hill function. Sometimes we'll use other forms. We might use exponential or tanh or other shapes, but our go-to functional form when we have activation and inhibition is going to be Hill function. And so we're going to start out by just looking at this diagram, which is a chemical A modes production of itself. And I want to walk you through the steps to take this diagram, which doesn't look like mathematics, and turn it into soluble mathematics. And this is something that we can do in a pretty mechanical way. It doesn't always give you exactly what happens in the biology, but pretty often it does. And so we're going to start out by using Hill functions to represent activation. And so what does activation mean? Activation means that the more of the thing that is doing the activating, the more of the product we get, or more specifically, the more rapidly we produce the product. Assume that for chemical reactions, we're either going to get mass action or Michaelis. There's a typo, it should say or Michaelis-Menten, not of Michaelis-Menten. For chemical transformation, and we're going to use Hill functions for regulation. So very often in the literature, you'll see something like what is in Herbert's problem. You say that chemical species A, there's my cursor, chemical species A upregulates production of S2. That is equivalent to a chemical reaction, which is that nothing goes to S2 at a rate that is dependent on A. And so the more A we have, the faster we produce S2. And that can be written as nothing goes to S2 at a rate which is a Hill function of A, V max times A to the n over K to the n plus A to the n. If I know what my source is, S1 goes to S2 at a rate that's regulated by A positively, I would say S1 goes to S2 at a rate V max times S1. That's the mass action law by itself, times A to the n over K to the n plus A to the n. That's the Hill regulation. And so S1 goes to S2 at a rate V max times S1. That's the chemical reaction rate, modulated by A to the n over K to the n plus A to the n. In this case, I've used Michaelis-Menten instead of mass action. K sets the concentration of A at which the reaction reaches half of its maximum rate. That's pretty convenient if we're going to couple reactions to each other. Almost, if we make sure that all of our Ks match, then we can basically couple reactions together without worrying about the values, just the way we would if we were using digital logic. So I strongly recommend that you pick a value of capital K and stick with it when you start out. I often use 0.5 because that way the values of A will go between 0 and 1 typically. They're allowed to overrun a bit on the top, but not by much. For inhibition, the more of the molecule we have, the less production we get. So here we see R inhibits the production of S2. We interpret that as nothing goes to S2 inhibited by R. Nothing goes to S2 at a rate V max. Instead of R to the n, we have K to the n. That's a decreasing Hill function over K to the n plus R to the n. Same thing, if we have S1 being converted to S2, S1 goes to S2 at a rate V max S1, K to the n over K to the n plus R to the n. If we assume Michaelis-Menten, we'd have V max S1 over Km plus S1 times K to the n over Kn to the n plus R to the n. Notice K to the n over K to the n plus R to the n is always between 0 and 1. And so this is always going to slow down the reaction. Really, that's all we need to know to be able to write some pretty complicated chemical reactions and regulatory circuits. The thing that we don't know how to do is if we have two arrows coming in modulating the same thing, if we have an arrow, a rate that's inhibited and activated at the same time, we have to decide how to combine those. And for that, unfortunately, there's no universal answer. That depends on the biology. We're not just in digital logic, but it's pretty close. Okay. That was for a signaling network. If we think about the same thing as a gene regulatory network, here we have P1 activating P2. What that really means is that P1 binds and promotes the transcription of gene P2. Again, that turns into nothing goes to P2 at a rate dependent on the concentration of P1, which is our classic nothing goes to P2 at a rate of a velocity that depends on P1. Same thing as before. For gene regulatory networks, we actually always have to infer that there's decay. Otherwise, we're going to get an infinite amount of P2. And so when we write P1 promotes P2, we have to remember that there's an unwritten arrow that is P2 decays to nothing. And so actually, this single lollipop arrow, P1 promotes P2, turns into P1 binds to the promoter, turns on gene 1 that produces P2, P2 decays to nothing. We have to always remember to write that. And so this is a little bit like learning how to spell in English or how to write characters in Chinese. There are rules, but not everything that you need is written. Sometimes there are things that you have to know in addition to what's written. The good thing about this is that it's pretty regular. There are not as many exceptions to the rules. There'll be a few, but not many, as there are in English. So if I'm going to do gene activation in terms of Hill functions, again, I start out with P1 promotes P2. I interpret this as P1 binds to a promoter, turns on P2, which then decays. We have two rates, the Hill function rate, V1 of P1, and the first order decay rate, V2 of P2. The trick for gene regulation is that even when genes are not turned on, they may have what's called a basal rate of transcription. They may be turned on at a low level because it's like a leaky faucet. And so the Hill function may not be just V Pn over K1 plus Pn. It'll be that plus a small leakage term, B1. And so it's usually useful to explore what the effect of that basal transcription rate is on your dynamical system. We'll normally assume first order decay kinetics. V2, the decay of P2, is just proportional to the decay rate times P2. Again, we're going to go through this relatively fast today, but you'll have plenty of, it's in the textbook, and you'll have plenty of time to refer to the slides and also practice it in the homework. Okay. So I can now, starting out with just the arrow diagram, P1 promotes P2, and the statement that it's a gene regulatory diagram, I can immediately write the full set of equations. B1 plus Vm1, P1 to the n over K1 to the n plus P1 to the n minus KD2 P2. It's sometimes convenient to do a little bit of rescaling. If I rewrite the Vmax equal to K1 times KT2 and C equals B1 times K1, C1 times KD2, then I can get things to scale out. In this case, I've basically just written everything in terms of the decay rate, KD2. And the reason I do that is that I can scale out time. I can measure things in time in units of decay times. And it simplifies, it eliminates one of the variables. In mathematical biology, we typically always try to eliminate extra parameters. This is one way of doing that, scaling out a parameter. So I can rewrite in this form, dPdt is equal to C1, KD2 plus K1, KD2 again, the Hill function minus KD2, P2. Why is that useful? Well, if I want to find the steady state, I set dP2 dt to 0, and that means I can divide through by KD2. It has no more effect on anything. And I get the steady state. P2 star is C1, that was my basal transcription rate, plus K1, P1 to the n over K1 to the n plus P to the n. I just get the Hill function. So the amount of P2 I get is just a Hill function of the amount of P1, which is what I would expect. Notice that everything is shifted up or down by that C1. Okay. This is just a restatement of that. For inhibition, I can do exactly the same thing. I still have that basal transcription rate. Even when I try to turn the gene off, it doesn't turn off completely. I go through exactly the same derivation. I don't want to walk you through everything I've just done. And I'll get a decreasing Hill function for that. So now, from these arrow diagrams, I can write down reasonable hypotheses about what the functional forms are. And then I can do something that I can actually solve numerically. Now, I should be careful. I should see what happens if I change the value of capital K. I should see what happens if I change the basal transcription rate. I should see what happens when I change the Hill exponent. If I'm very sensitive to those things, then probably I made some mistake. But functionally, I've got these two things, and I could understand this in some ways as a Boolean switch. If K1, if a P is less than K1, it's off. If P is greater than K1, it's on. If P is intermediate, then I have some intermediate state. Again, if I see P1 promotes P2, this is for the homework. If I see P1 promotes P2, I write this as nothing goes to P2, promoted by P1. That gives me a rate P plus V max P1 over K, the N plus P1 to the N. Again, the nice symmetry. If I have inhibition, I just replace that P1 in the numerator with K. Usually for gene regulatory networks, things are pretty much on or off. So I'll typically use N equals 4 or N equals 8. So now based on that, let's do that. So why don't we do a couple of exercises on autocatalysis. See whether you can, if you need the slide deck is in the student materials folder, so you can download it. Or see if you remember how to do it. The first step is, why don't you take this and write down the rate law for the production of A based on this diagram. I think you can, does that make sense, the question? Based on the rules we just described. Niraj wrote it down. Okay. Chen, were you able to figure, did that work for you too?
Yeah, I'm trying to run it.
Oh, you're already running it. You're ahead of me. Okay. So that was what I got. Herbert likes to use a value of K of 10 instead of 0.5. So I use 10 because that's what he uses in the textbook here. You'll need to pick initial values for the simulation. I suggest B equals 0.2, K1 equals 2, K2 equals 0.1, and H equals 4. And again, I'm giving those values because those are the ones Herbert uses in his example. And what's interesting for this one is if you change the initial value of A, you'll get different results. So I guess I took the surprise away by hitting space, but here I've scanned the initial values of A. And what I see is that there are two fixed points. If I start with a low value of A, I go to a low fixed point. If I go to a high, start with a high value of A, I go to a high fixed point. This is our first example of bistability, or bifurcation. If I start with an initially low value of A, I go to a fixed low value. I start with an initial high value of A, I go to a fixed high value. So why don't people try that? Make sure that that works for you. Let me know if that works for you, if you need more time. If it doesn't work, need an explanation. So if you play with it a little bit, you can sometimes find the intermediate value where it stays right in between, doesn't go to either the high or the low value. That's called the unsteady fixed point, the unstable fixed point. So you have two stable fixed points, a low value and a high value, and an intermediate unstable fixed point. We could do the full bifurcation analysis analytically if we wanted to. In a more mathematical biology course, that's something we do. All right. Now, why don't we use the code that we've written before and plot the steady state value as a function of the initial value of A. And transform the code that you have here pretty easily to do that. Just the way we found the get steady state values before. In this case, I wouldn't recommend using the get steady state value, though. I would recommend using the just running it for a long time to get the final value. So maybe I'll ask it again later, but you might think about what this circuit might do functionally. You possibly, of course, biological systems aren't designed, but if you were designing a biological system, what would you use this circuit to do?
So it might be something like one cell type give two different cell type on the basis of a protein concentration.
Yeah, you could use it for differentiation.
Yeah.
Fundamentally, this is a memory circuit. It's a 1-bit memory. If I force the value of A high, the value of A stays high. If I force the value of A low, the value of A stays low. So in this case, the circuit is able to remember whether the earlier values of A were below the threshold or above it. So effectively, I have a 1-bit memory here. Now, if I were to simulate this as a stochastic system, which it really is, I would find out that it's a lossy memory, that the system forgets itself after a while. But we're not going to do that. If you want to see what happens when you have a lossy version of this, we haven't done it yet, but I'll type it in the chat. If you type, instead of r.simulate, you type r.Gillespie, and then the initial time, the final time, like this, no number of points. That'll run the simulation stochastically. You'll see how different it is. We won't really do that for a week or two, but it's sort of fun for the circuit, so you might want to try that. So you can use the steady state parameter scan that we just wrote, that we used in the previous exercise. You can use that here. Again, except instead of using get steady state value, I'd just run the simulation for a long time. See what you get. So you have a very interesting result here. So in your example, Jen, you ran it for a finite amount of time, right? You ran it for a fixed amount of time before and then calculated the value. Is that right?
I just called the get steady state values function.
It did. Okay, what was the step size you used for your initial value of A?
The A naught is ranging from 0 to 40, and the step is 1.
Sorry, the step was 1, did you say?
Yeah. Yeah, the
Okay.
step is 1, yeah.
Could you run it again where you make the step size a little smaller? Make it 0.1, for example. See what happens. I'm a little surprised it got stuck in that intermediate range like that. Yeah, the get steady state value isn't returning quite what you should expect it to return. A little puzzled by that.
Takes a long time.
That I believe. Let me look at what I got while you're doing that. Yeah, no, it definitely is finding that it's getting stuck on that intermediate state. So that's telling you that the get steady state value is actually not really getting a steady state value. It's getting an approximation to it.
Okay.
There's some tolerance in the get steady state value. In reality, what you would expect is it should be low and then shift abruptly to being high.
Okay.
You shouldn't get that intermediate ledge. And that's not you. That's a computational problem.
I see.
But that's certainly the basic idea. You expect that for small values, initial values, you get the low final value. For large initial values, you get the high final value. Puzzled why the initial value of 0 to 5 gives you 0.25, an initial value of 15 to 10 gives you a final value of 2. Something seems slightly off to me about that. But conceptually, it looks fine. So the last thing that I wanted to do, and this is just a little bit trickier, but works in the same way, which is suppose that we now change one of the parameter values and plot that high value and the low value. So here I've started with initial value of a equal to 0, or some small value, maybe a equals 0.1, and a equals 20. I've run it for a long time to get the final value. And now I've scanned not the value of A, but the value of B, K1, and K2. And these are what are really are classical bifurcation diagrams. And so let's just look at the B one for a second. If B is very big, what does that mean? What did B represent?
The basal rate.
Right, the basal rate of transcription. So if we have a high basal rate of transcription, what's going to happen to our circuit? Is it going to care what the initial value of A was?
No.
No. If I have a high rate of basal transcription, the circuit's always going to turn on. It's a leaky circuit that's always going to turn on. And that's what I'm seeing here in this bifurcation scan B. If I start out with B equal to 0, then for low value of A, I stay low. If I start with a high value of A, I stay high. As I increase the value of B, that low value drifts up, the high value drifts up. But if I make B too big, no matter what my value of A is, I always wind up with a high value of A. What about K2? K2 is sort of interesting. K2 is the decay rate. Suppose that I have a high value of K2. The chemical decays very, very quickly. What is that going to do? If A disappears very fast,
So ideally it won't activate itself.
well, if A disappears very fast, it's not going to have time to turn itself on. And so I'm going to wind up with no A at all. And so if K2 is too big, the circuit is always turned off, no matter what the initial value of A is. And so these are three bifurcation diagrams that you can plot. So why don't you try, that's the last thing we'll do today. We actually have a little bit more time, so maybe we can get through this in one more thing, but I'd like you to try this. Start with, so here's what I'd like you to do. I'd like you to start with a high value of A, that's always compared to 10. So start with a initial value of A of 2, initial value of A of 20. And scan the value of B and plot the two final values that you get. If A is small initially, if A is big initially, see if you can reproduce these three curves. Once you've reproduced one, you simply change, instead of scanning B, you scan you scan K1 or K2. Notice that the ranges over which you have to scan them are a little bit different. So to see the bifurcation, and for B, you have to scan it between 0 and about 1. To see the bifurcation in K2, you have to scan it between 0 and about 0.2. And to see the bifurcation in K1, you have to scan between 0 and about 2 or 3. And if you get frustrated by it, I've got a Colab notebook here, 5.7.4. You could try it out, but give yourself a few minutes and try this out. Because if you can do this bifurcation analysis here, there are really only one or two more things that you have to be able to do pretty much analysis of almost any circuit. So why don't you take 5 minutes, 10 minutes to try to do that. Give you the code for one of them. Oh, you got it. There we go. Niraj.
So for the bifurcation analysis for K2 value, do we also change the A value?
Well, you always have
like
to.
what should be the initial A value?
Well, for both of them, you need to start with one high value of A and one low value of A.
Okay.
And high and low are determined by the value relative to the 10 in the Hill function. You could start with a value of 2 and 50, for example, would do it. Dan, was it working for you, or you need?
Yeah, the parameter, if the A is large enough, I got the correct result. But if A starts from like 5 or 10, the solver just doesn't work.
Yeah, you've got to pick an A value that's substantially bigger than 10. So the low value of A has to be much less than 10, and the high value of A needs to be quite a bit bigger than 10. So you start with something like 2 and 50 to get the two branches.
Okay, but if I set A as initial A as like 2, the solver says possible negative concentrations in solution.
Is that
I'm still using the get steady state values function.
Yeah, I would try. I wouldn't use the gets. Shouldn't.
Okay.
It's maybe for the that's when you're scanning K2.
I'm scanning B.
B.
Yeah.
And it says that you get negative solutions.
Yeah, the possible negative concentrations.
Sounds like a bug in the steady state solver to me, because there are no negative values on that one. So I don't know why it's doing that.
Yeah, can I see the notebook?
Sure. I was just going to put it in the chat for you. And one thing you may find if you run for a finite amount of time, here I ran for a time of 150, is that it may smooth out the bifurcations a little bit. And so in that case, you may want to try changing the simulation time to be 300, 500, even 1,000, and make sure that nothing changes in your result. So yes, if you look at the value of A, R.A, after you've run simulate, it'll give you the last value. Did that work for you now?
Yeah, it all works.
Okay, great. I was just noticing the K2 one. There's a little bit of a trick that you have to play, which is if you want to run it for a long amount of time, for small values of K2, I'm sorry, the B one, for small values of B, sorry, I said, got it labeled wrong here. It should be K2. K2. For small values of K2, the value diverges. And so you have to actually not auto scale the x-axis, the y-axis, to be able to see the bifurcation. So that's actually doing some real bifurcation analysis. We haven't talked much about the mathematics of bifurcations. If you're interested, we can do that. The analysis is done out pretty much in detail in one of the basic mathematical biology textbooks like Murray or Britton, if you want to look, or any dynamical systems textbooks. But this is a particularly nice one because it is a circuit that we see over and over again. And you'll see in the at the end of Herbert's textbook, one of the appendices, which I asked you to read, talks about how to do bifurcation analysis. And we can do that analysis ourselves as well. It's not a hard analysis for this particular problem. I would like people to, did people have a chance to look at that example of Moen's at all that I handed out, the paper of Moen's that I handed out? I had started writing a notebook for that, but I hadn't finished it. Now let me just show you what I did quickly, so you can see where I was with that. So in this case, and I've shared this. I'll share this folder with you as well. It's not complete, so maybe you can help me work on it. I went into Moen's paper. He has an initial model, which is this one here. And as I mentioned, it's not so easy to determine what the molecular circuit is. He draws it, but he draws it in a slightly odd way. So I just wrote the differential equations directly, which I don't like doing, but that was the fastest way to do it. In Antimony, this is typing the differential equations directly. And he gives you a table of all the parameter values, or a lot of them. And I put them in here. And then he has two additional equations that make the thing oscillate. So I ran the first set of equations. And for the parameters that he gives, they reach a steady state. Actually, I don't know 100% if they reach a steady state. I think they do. Let's see. Reload Tellurium. Colab isn't running very fast tonight. Okay. Now I'm going to load my model. And it reaches a steady state. Now I'm going to add these two additional equations. And we can talk about what these mean in P53 oscillations later. But I'm going to run those two additional equations. And, oops, not, skip the cell. And now with those 5 equations, I get stable oscillations. And now what I'm going to do is I'm going to put in an external sinusoidal driving term here. And now I'm going to get an interaction between the driving term and the internal oscillations. And this is going to give me, this one gives me a chaotic time series. Now what I wanted to do was write code that would tell me whether the series was chaotic, periodic, and if so, what the frequency of the period was. And that's what I hadn't finished doing. It's relatively straightforward to do that, but I haven't done it yet. So that's where I was with that. And so I'd like people to try to think about that, not just doing the math, but actually thinking about what it means. I think that's a nice problem set. And, it'll give you a lot of practice trying to understand bifurcations, periodic oscillations, and questions before we break for tonight?
I have a question, like in
Sure.
this, so you gave some external signal. Is that something similar to perturbation?
Yes, it's a periodic perturbation in this case.
Okay.
So if you look here, where is it? This one. Where's the one I want here?
Above the graph.
So the top one, TNF, is the periodic oscillation. So it's a periodic sinusoidal driving.
Right.
Yeah, I actually have a question about that. I don't know how you can like implement the oscillation in real life, in real world. Like how could the concentration vibrate or oscillate?
Well, so the system in reality does oscillate on its own. So even without the external forcing, which is this one here, the P53 will oscillate. Now, it depends on we're jumping into the middle of this, which is why I asked the questions I did in the homework. P53 is a signal that induces repair of DNA damage. And so when there is a DNA damage signal, P53 gets turned on. And it's actually not so much the level of P53, but the location of P53, whether it's in the cytoplasm or the nucleus, oscillates. And the frequency and amplitude of those oscillations depend on the amount of DNA damage. If the amount of DNA damage is high, you get big oscillations. As the amount of DNA damage goes down, the amount of P53 goes down and the oscillations turn off. Here, we're assuming that we essentially have a fixed amount of damage, that there isn't any recovery. Otherwise, we'd have a continuous decay of one of the things driving the system. Now, what they did experimentally and is not apply a sinusoidal driving, but they put a chemical into the environment of the cell that pushed P53 up. And you can do that in a pulse. And you can do that at a steady frequency. So essentially every 10 seconds or every 10 minutes, you put one drop of the chemical that drives P53 into the dish, then you wash it out, put it in again, and you wash it out. So it's possible to actually drive P53. You can't give a perfect sinusoidal driving, but you could give a pulsatile driving. And one of the things that he investigates actually in the paper is whether it matters whether you have a sine wave driving or a pulse drive. And we could definitely do a pulsatile driving here in the simulation. I just didn't have time to implement that yet. Now what's missing in the analysis in the paper that he presented there was why why that oscillatory behavior of P53 might be interesting biologically. And so his current graduate student is working on that. And it winds up that the frequency of oscillation of P53 makes a big difference to how efficient DNA repair is. If P53 oscillations are too slow or too fast, DNA repair is not effective. And that's from a different mechanism, one that's not included in this model, but it's included in his more recent papers. So I think those are great things to discuss, and I think let's talk about them next week. I've shared this notebook with you. It's not, as I say, it's just a beginning notebook. I was just beginning to work with this myself, but one of the things that we need to figure out how to do is how to estimate the frequency of oscillation of the two frequency of oscillation of TNF is easy because that is controlled, but how to estimate the frequency of oscillation of the response of the NF kappa B, which is NN here. It's a little bit harder. The way I tried to do it, which was to do to count the peaks, won't work for this one.
I mean, you can just use Fourier transformation.
Right, I should have used the Fourier transformation.
But why? Why you didn't?
Because if the oscillations are regular, then counting peaks works just as well. When you see period doubling, it also works pretty well. I should have used the Fourier transform one, and in fact, if I had asked it, if you use this instead of saying period, as I say, use frequency for their self-generate one. It'll do the Fourier transform one. So I would try. Why don't you try that? See if you can get the Fourier transform one.
Okay. But I don't have the link. I mean, you didn't put the link in the chat.
The notebook is in. I can put the share one in the chat too.
Yeah, sure.
But it's in the student materials folder.
Oh, I see.
But let me give it to you directly here. I'll give you the link here. There.
Okay, thank you.
Yeah. This is a pretty rich problem. I mean, one could spend a lot of time on it. I mean, Mons has spent 15 years of his life working on this problem. It's not a trivial problem. Part of the reason, as I say, that I like it so much is that he's addressing something that I worked on with him 40 years ago in my very first paper. And it's something I never came back to and that he came back to many years later. And so to me, it was fascinating to see that when we were working on it, we weren't doing it in a biological context. And so it was fascinating for me to see something that we had studied in the context of fluid dynamics show up as a biologically meaningful result. So, but yes, let's switch that to be the Fourier analysis, and then we can see better. What you want to plot basically is what you really want to plot is the driving frequency on the x-axis and the response frequency on the y-axis. And instead of being a straight line, which would be case for a linear system, you'll get steps.
Yeah, yeah.
And it's those steps that we want to analyze. Okay.
Yeah.
Great question, and great.
Yeah, because I have done a lot, like in my master program, like this kind of frequency analysis.
Yes, well, quantum, when you do a Josephson junction works this way.
Oh, my master program, the research topic in my master program was not about quantum computing. It's about magnetic field and the like how the materials will respond to the driving external field, that kind of thing.
Oh, so you have so yeah, so the susceptibility
Yes.
is a function of driving frequency.
Yes.
Yeah, that goes back to Alfvén waves, which were a topic of. I mean, there are plenty of modern topics of research too, but Alfvén waves won a Nobel Prize in the 1950s for seeing that kind of frequency locking. So yes. So it happens both in classical and in quantum systems, and in biological systems as well, and in fluids.
Yes.
So frequency locking is a very universal phenomenon.
Yeah.
Okay. Well, that's pretty neat. You'll have to send me a paper about the kinds of things that you were doing in your master's degree. I'd love to see that.
Oh, I published a paper about that.
Great. Send it to me, please.
Yeah, sure. I can give it to you right now.
Okay, that would be great.
Okay, I will definitely read that. I look forward to that.
Okay, thank you.